Hi students, welcome to a video on control system. In this video we will see MATLAB codes to realize transfer functions. Okay, let us see these basic slides. Okay, if you are ready, we'll start. So now we shall have a look at this now. So this is a very simple feedback system having GFS as the forward block and HFS as a feedback block. So let us consider GFS as 10 by s plus 2 and HFS as 1. Let us consider a negative feedback. We know that open loop transfer function is given by GFS into HFS. Upon doing that, we'll get 10 divided by s plus 2, which will have a pole at minus 2. And the closed loop transfer function is given by this equation for a negative feedback system. So upon substituting the GFS and HFS, we will end up with 10 by s plus 12, which will indicate a pole at minus 12. We will write the code for this representation in the MATLAB and try to locate the poles at minus 2 for open loop transfer function and at minus 12 for closed loop transfer function. So let us straight away go to the MATLAB code. Okay, this is the MATLAB code which is representing the numerator of G, which is 10, the denominator of G, which is s plus 2. I hope all of you have written this transfer function. Please make a pause of this particular video now. Please write the open loop transfer function, closed loop transfer function, so as it is being written here. So then after you write it, let us proceed. So let me go here. Now you can see we are writing as you have already written the numerator and denominator of the G and H. This is the numerator of G, which is 10, denominator is s plus 2, and for H it is 1. We are trying to find the open loop transfer function, which is GFS into HFS. We are using a function called series, which is actually multiplying GFS and HFS, and that numerator denominator is assigned to numerator OL and denominator OL, that is these two variables. And we want to write the system open loop transfer function in the form of S. So upon doing this TF, that is converting that numerator denominator to transfer function, so we use a function TF of numerator denominator. So this will actually return, if you can see here. So I have already ran it once, so this is what it is returning. Okay, let me run this. If I run this now, it will actually give me the numerator. Okay, system OL has got 10 by s plus 2, which is the open loop transfer function, and the corresponding poles are at minus 2, there is no 0, and there is a pole at the root locus gain is 10. So upon doing this, okay, now ZPK values of the open loop transfer function are these ZPK values. Z is not there, P is at minus 2, K is 10, and this is actually plotting me the poles and zeros. If you can carefully note that, okay, this is only one pole at minus 2 as the X value, and Y value is almost 0. So that's what is a pole at minus 2, and we are doing a feedback with negative feedback as minus 1. Whatever numerator denominator will get, so that will be numerator closed loop and denominator closed loop. We are writing the transfer function of the same numerator denominator using a function TF. So which you can see here, this is what is that system CL, which is 10 by s plus 2, which is there we saw over here. So this is what we saw here. This is 10 by s plus 12, s plus 12. So this is what we saw in the closed loop transfer function. So this is what is. Then we are trying to find out the poles and zeros of it. So there are no zeros, but there is a pole at minus 12, and of course the k value is 10. And we know that this is my closed loop transfer function. The pole is at, so if you carefully notice this, so this is a pole at, this is the pole. I can just zoom it out and then okay, let me run it again. You can see the pole is at minus 12. See here, this is the pole position which is at minus 12. Okay, this is fine. So now let us come over here, and as we have written, so let us replace this by k and keep on giving different values of k. Let us see how does a pole will move. So let us do that. Go here, let me define. Of course, let us say it as k is an input. Let me just enter k. Let me put it in colon. Okay, now this is in single quotes. If I run this, okay, now let me also replace this by k, or let me just, okay, now let me run this. Now it is asking for the value of k. Now you can give the value of k as around 0.1. If I give the value of k as 0.1, if you can see here, the open loop transfer function is at, so let me just, okay, sorry for that. Okay, this should be small k because I put it as capital K. It is case sensitive. Let us make it as small k. Okay, this can be anything. Okay, now let me run this. Now let me give the value of k as okay, 0.1. that's the value of k. The moment I give the value of k as 0.1, you can see the open loop transfer function is this is the value of k, and this is the pole position. You can see pole is at minus 2, there is no 0, and the k value is 0.1. Okay, you can see the closed loop transfer function, it is 0.1 s plus 2.1. The pole has slightly moved from minus 2 to minus 2.1. That's what you can see. So as the value of k changes, earlier it was at minus 2, the pole, now it has moved to minus 2 point something. Now let me give another value of k. Let us give the value of k as, let me give the value of k as like 100. If I give the value of k as 100, now you can see the pole has moved from, this is the open loop pole position which was at minus 2, now it has moved to minus 102. Basically what I mean to say here is, as the value of k changes, so let me just show you here. As the value of k changes, you can see this is the pole position. Pole position is keep changing from minus 2 to k minus of k plus 2. Suppose if the value of k is 100, the pole is at minus 102. If the k value is 1000, then it will be at minus 1002. So the pole which was at minus 2 under open loop transfer function will keep moving away from this minus 2 depending the value of k. So this is how it is moving. So let us see one more transfer function where you have something like this. So let us have a transfer function where you have two poles. One pole is at s plus 2 and other is at one is at minus 2, other is at minus 4. So the transfer function becomes k by s square plus 6s plus 8. So let me modify this, just keep this in mind. Please write this transfer function. It is k by s square plus 6s plus 8. So the numerator of g becomes k, the denominator of g becomes 1 okay, 1 space 6 and 8. So let me just go there and modify the code. So this is 1, 6 and 8. So let me keep giving different values of k for this. So as the value of k is let us see the open loop trans function where the poles and zeros are. So now if I give the value of k as around, now you can see I give the value of k as 10. If you can carefully note this is my open loop trans function, which is 10 by s square plus 6s plus 8. You can see this was k, now k is now replaced by 10, and you can see the poles are at minus 4 and minus 2, and there is no finite 0. And of course the value of k is 10. Now this is the closed loop trans function. The closed loop trans function is now, okay, let me just check out. This is the closed loop trans function. This is closed loop transfer function. Okay, now this is the closed loop transfer function which is given by this. Okay, now let me again give a different values of k. Let me give it as 10. You can see the pole has, if you can see, this was actually 8 for open loop trans function. Can you see this was 8, now it has become 18 as the value of k is 10 now. Now corresponding to which the pole which was there at minus 2 and minus 4 has moved to minus 3 plus or minus j3. If you can carefully notice this here, you can see this was the open loop pole position which was at minus 2 and minus 4. Now it has moved to minus 3 plus of j3, and this is minus 3 minus j3. So the poles have become complex, and of course there is no 0, the value of k is 10. Now suppose if I give a value of k which is bit less, so what I'll do is I'll give a bit lesser value of k. Let me give it as 0.1. If I give the value of k as 0.1, you can see the pole which was there at minus 2 and minus 4, which was the open loop trans function, has now moved to minus 2.05 and minus 3.94. Actually what's happening now is, suppose if you just notice this, the pole which was there at minus 2 and minus 4, the pole has actually moved to this and this. If you further increase the value of k, it will come here, it will come here. For a particular value of k, both the poles will be there on minus 3. If you further increase, this will go like this. If you further increase, it will go like this. If you further increase, it will go like this. For larger values of k, the poles are always at minus 3 plus or minus jx. So this x can be keep increasing, this x can be keep increasing, but you can see this is exactly at minus 3. So the poles will be keep always moving away. Okay, they are on the imaginary, they will become complex, and their real part is always minus 3. So that is what is one thing you have to observe. So let me go here. I have given the value of k as 0.1. It is still at it's at minus 2.05. This is at minus 3.9 something. Suppose if I run it again, if I give the value of k as 100, just notice this. Is this now minus 3, but it is the g value is increased to minus 9 something. If I give the value of k as something like maybe 1000, if I give the value of k as 1000, you can see it is still minus 3, and if you can see this is moved from 9 point something to 31 something. Suppose if I again run, and give it as maybe 5000, if I give it as 5000, carefully observe, this is still at minus 3, this has become plus or minus j70. That's what I said here. here I said that okay, this real term is always -3, but the imaginary term is keep increasing as the value of k is increased. Now let us introduce a 0 and then try to find what happens to the. See, now what we're trying to do is, this is a transfer function. I will introduce a 0 here. I'll introduce a 0 here. Let us see what happens. So there is a 0 at -1. Let us retain the same transfer function and try to see what happens to that. So what will be the numerator of your g now? So ng will become, k times, okay, now it is 1 space 1. So this is actually representing ks plus k, which will have a 0 at -1, and there is a pole at -2, and there is one more pole at -4. Let us see what happens to the pole positions as the value of k increases. So now this is the open loop pole and 0 position. A 0 is at -2, poles are at -2 and -4. So let me just go here and then try to, let us see, is it okay? It's fine. Okay, where is this? Let me go here. This has to be modified to k multiplied by, this should be 1 space 1. So this is actually introducing a 0 to the system. The moment I run this, since it is asking for the value of k, let me give the value of k as 0.1. As I give the value of okay, sorry, this is not yet saved. Let me first save this. Okay, now let me just see. Now this is the pole position. We have given the value of k as 10 now. As the value of k is 10, so the open loop transfer function becomes ks plus k, which is nothing but 10s plus 10, and of course this is s square plus 6s plus 8. There is a 0 at -1, there is a pole at -2, -4. This is the open loop poles and zeros. This is the open loop poles and zeros. Once you close the loop, so this will become 10s plus 10, s square plus 16s plus 18. Take time and then try to find out what is the closed loop transfer function. So let me just tell you, for k is equal to 10, so g of s becomes 10 into s plus 1 by s square plus 6s plus 8. h of s is equal to 1. Then closed loop transfer function cfs by rfs, which is nothing but gfs by 1 plus gfs into hfs, will be the same. The overall simplification of this is the same as gfs s square plus 6s plus 8 plus one more term. That term is gfs into hfs. So of course numerator of gfs, which is 10 into s plus 1 into hfs is 1. So this becomes so and so, and this is s square plus, this is 6 plus 10, 16s plus 18. This will be my transfer function. So this is system closed loop. This is the system closed loop. So let us keep an eye on this. Please write this transfer function and then have a look at this. Can you see, is this not 10s plus 10 by s square plus 16s plus 18? This is as per this. Okay, now let us stay on the page. Tap into this. Let me just minimize this. See, now this is the transfer function. This is 16s. You have this, and if you find the roots of this, of course you can use calcium, then find the roots. The 0 is still at -1, and pole has moved from minus. Of course, actually the poles were there at -2 and -4. if you can see here, this pole has moved to minus 1.21, whereas this has moved to minus 14.7. Let me increase the value of k to a bit larger value. Now you can see, let me enter the value of k now as 100. As I increase the value of k to 100, see now this pole has become, of course this is my closed loop trans function. It is now 100s plus 100. Now it is 106 s square plus 106 plus 108 is the denominator. The roots of this is giving pole at minus 104 and minus 1 point something. You can see now this is going very closer to minus 1, whereas this is moving too far away from so and so. What we are trying to understand here is, this is minus 1, the pole was at minus 2, there was a pole was at minus 4. This was the pole positions. As you increase the value of k, this is keep moving towards the 0, whereas this is keep moving towards infinity. So this will, the pole which was there at minus 2 with the value of k as 0 will reach minus 1 as k is equal to infinity. Since it has only one finite 0, it will terminate in 0. That is, the closed loop pole will terminate in 0. The other closed loop pole will terminate in infinity, because there are no more finite zeros. And let us now see, let us introduce two zeros and to this, and then try to see now. So where are poles and zeros now? So there is a pole at minus 2, there is a pole at minus 4. Let me introduce a pole at minus 1, which is already introduced. Let me introduce this at minus 5. So now my transfer function becomes k into s plus 1, s plus 5. This is s plus 4 and s plus 2, which will be k into s square plus 6s plus 5, 6s plus 5. This will be s square plus 6s plus 8. So let me modify the transfer function, try to see what happens to this. So this is now 1, this is 6, 5, and this is 6, 8. Okay, fine. So this is actually giving this transfer function, or introducing two zeros at minus 1 and minus 5. If I run this now, I'll run this. The moment I run, okay, let me give the value of k as 0.1. If I give the value of k as 0.1, see where the poles are. Is the pole which was there at minus 4, has it gone to minus 4.1? So has it moved here? Is it not minus 4.1? Has this which was there at minus 2, has it gone to minus 1.8? This is for the value of k which is very small, which is like 0.1. So now let me again run it now. Let me again run, and okay, let me run this. It will ask for the value of k. Now when I give the value of k as like, okay, 10. Now where is the 0? Can you see the the pole? Of course, zeros are there at minus 1 and minus 5. You can carefully observe that if you change the value of k, the 0 position which was there at minus 1 and minus 5 for open loop trans function. You can see this is the open loop trans function 0 on pole position, minus 1 and minus 5. And if you see the pole position minus 2, minus 4. This is the open loop pole position, open loop 0 position. This is your open loop pole position, that's at minus 1, minus 5 and minus 2 and minus 4. The closed loop pole, if you carefully observe the closed loop zeros, it is still at minus 1 and minus 5, but you can see the closed loop pole is going towards minus 5 and it is going towards minus 1. Can you see, has it gone here? If you carefully note this, has this gone here? Has this come here? As the value of k increases, this is moving towards the finite 0. This is also moving towards 0. That was for a value of k which is maybe it was 10. It was 10. So now let me run it again and try to see for a larger value of k. Where did I enter? Okay, let me again run this. Let me make the value of k as 100. See now, as the value of k is now 100, can you see it's almost there at 0 position. This is almost gone to -1. So let me give another value of k which is maybe 1000 or 10,000. See now, has it almost there at this position? Has it almost gone to -5 and -1? The point what we are trying to stress here is, as the value of k is keep increasing, can you see it has gone to -5 and -1 for large value of k. So now the point here is, as the value of k is keep increasing, as the value of k is keep increasing, the open loop poles will try to move towards the open loop 0 position. Open loop 0 position. If the 0 is there at a finite value, it will go there. If it is not there, it will go to infinity. Now let us take the same example. Let us have it as -2 and -4. Let us have this at plus j3 and minus j3. Let us have the zeros at the imaginary axis. So this becomes k s plus 3, sorry, s plus or minus j3, and this is s square plus 6s plus 8, which is nothing but s square plus 3 square, which is now s square plus 6s plus 8. So then this will be s square plus 9, whereas this is s square plus 8s, sorry, 6s plus 8. So let me edit this, and where is my program? Okay, let me just go here and make this as 0. Now I have to make s square plus 9, so this should be 9. Now let me run this. Again, it's asking for the value of k. Let me give the value of k as maybe 0.1. If I give the value of k as 0.1, can you see it's almost at -4, and so the poles are still at almost at -2 and -4. If you can see this has slightly moved. So this has slightly moved to -4.1 here. So now this is, it's -1.8. Now let me increase the value of k to a larger value. Sorry, this is not yet altered. Let me just sorry, this I need to change this 10 as entered here. Now let me run this. Give the value of k as, see now, so this is the open loop transfer function, which is 10s square plus 10, because I have given the value of k as 10 now. So it is now s square plus okay, s square plus 9 was there. Now into 10 will become 90. You can see this is my open loop 0 position, that is j3 and minus j3. The poles are at -2 and -4, -2 and -4. So upon closing the loop, because this is the pole position and this is your 0 position, you can see 3i and -3i, and the moment I close the loop, now the 0 is still at plus or minus j3i. You can see the pole has started moving towards the 0. Can you see this is your pole position? You can see this is the pole, now it is at minus 2.9, so on so. If I slightly reduce the value of k, what I'll do, I will give a reduced value of k, which may be, okay, let me just run it again. So let me give it as 0.1. Can you see it's there here? Can you see this is the pole position? This is a pole position minus 2.7, but it will come to this minus 3. This will go to plus this 3. So this will actually go there. This will actually come here. If you further, okay, let me run it again. If you give the value of k as 1000, you can see the pole which is there at minus 2 and minus 4 will tend to be reaching. Now I have given the value of k as 1000. So now for a larger value of k, this will almost come close to this, close to this. You can observe that. Can you see here? If I run it, see where this has gone. Can you see it's almost there at minus, this is the imaginary value. Can you see it has become almost 3, this is minus 3. The real part is very close to 0, it's very close to 0. So this way we can see the pole positions will, open loop poles will be moving towards, of course the closed loop poles will move from open loop pole position to the position of the 0 as the value of k increases from 0 to infinity. If there are no finite zeros, the closed loop poles will terminate at infinity, or if there are some finite zeros for larger values of k, closed loop poles will terminate at the 0 positions. Thank you.